Hi, and welcome to this talk about Libp2p. So Libp2p, as the name implies, is a library which helps you build peer-to-peer applications. And more than library, it's also specifications on how to implement this library, because this library exists both in Nim, obviously, but also in Go, Rust, JavaScript, etc. So first of all, nice to meet you. My name is Tanguy. You might have seen me around on GitHub or Discord. I'm a software engineer at Status and one of the Nim Libp2p maintainer. And so the first question we're going to ask ourselves is, why do we want peer-to-peer? And so to answer this question, we're going to take a look at the simplest form of networking you can have, which is a client-server model, in which you're gonna have a device, for instance, your laptop, your smartphone, or whatever you're using right now, which is going to request this video from the YouTube server, and the YouTube server will send back the video. It's pretty simple, pretty straightforward, seems pretty nice. Now, if we zoom out a bit, there are actually multiple of you, or at least I hope so. And so you're all gonna request the file from the same server, and the server will send you back the file. And so we can start to see a few issues with this model. First of all, this server is gonna get more and more expensive as more and more people use the service, because you're gonna need more bandwidth, more CPU, more RAM, more storage, etc. So your server is gonna get very expensive, up to a point where you won't be able to get a more expensive server just because it doesn't exist on Earth. And so your service is not going to be able to scale well enough. Also, if this server is in America, for instance, and you are in Europe or in Japan, since you are far away physically from the server, it's going to take you longer to talk with him, and you're going to have a lot of latency issues. If this server goes away because of a power failure, networking failure, hardware failure of any kind, your whole service is gone, so YouTube would be gone also, so it's not very reliable. And since this server is held by a single company, YouTube or Google in this case, they can use the data you give them to them by using the service and do whatever they want with it, so it does pose privacy issues. And finally, if Google or YouTube start to censor things, for instance, if they remove every French video from the site, I will be gone quite quickly, so it's also prone to censorship. So, if we switch to peer-to-peer, it looks very different, obviously. Everyone is at the same time a server and a client, and everyone is talking with other peers and exchanging data. So we can see that with this model, we fixed a lot of issues we had with the client-server model. So first of all, there is no single server in the middle, right? So you won't have an expensive server because you don't have a dedicated server to run this service. And also, if this service is well designed, since every time someone joins the network is gonna give some power to the network, some bandwidth, some whatever, your network could scale and your service could scale automatically, and you won't have any scalability issue, if it's well designed at least. Also, you're more likely to have a peer which is close to you, because if some of you are watching in Europe, some of you in America, I don't know, you could share the file amongst you, and so you have better latency overall. If one peer goes away, the network is still fine, so you don't have reliability issue as much as with client-server model. And also, if one peer starts to censor some data, so if I block every video with French guys in it, you can still get the data from someone else in the network, so it's less prone to censorship. And finally, because there is no central server held by a single company, it can give you tools which helps you build system with more privacy in mind. But it's not like peer-to-peer networks are private by default, but they can be made private because there is no central entity holding all the data, basically. So that looks pretty good, right? Good. We seem to have fixed every issue with the client-server model, but it does come with one cost, which is pretty big, and that's complexity. Instead of just only one connection to one server, you're going to have to manage connection to a lot of different peers, which might have more or less latency, more be honest or dishonest, and so it's really more complex to build peer-to-peer applications. But it's really worth it, and actually if we go back to this slide, it was obviously a bit of a lie. Maybe 20 years ago it was common to have services which are running on a single server somewhere in a data center or at someone's house, but nowadays it looks a bit more like this. You have a private peer-to-peer network inside a data center where you have thousands or millions of servers talking to each other in a peer-to-peer manner, and then you just have some way to talk to one of these servers to get into this network basically, but you're not part of the peer-to-peer network. The peer-to-peer network is somewhere else, and you can just access it. So that's actually one example of peer-to-peer. What we call the cloud is generally some form of peer-to-peer for the same reason we seen before, so mostly reliability and scalability. But we're going to take a look at a few other examples which are noteworthy. So obviously, when I say peer-to-peer, you must be thinking about BitTorrent. It's like a pretty well-known sharing file system, which was actually invented in 2001 because the client-server model was too slow, especially back then when you had less bandwidth available to you. It was very slow to retrieve files from a server, especially if multiple people were trying to access the same file. So BitTorrent was built to fix this issue, basically. So you have maybe already seen this while playing a video game. So a lot of games are using a peer-to-peer network inside a match. So when you are entering a match, you're going to connect to other players in this match, and this way they can save on server costs basically, and also latency issue. If you have a lot of players near you, you can just connect directly to them instead of going to a far away data center. Skype also is a very good example of peer-to-peer. When you call someone, it's gonna generally try to establish a direct connection between you and the person you're calling to exchange data directly between the two of you. Again, better latency, less server cost, etc. So this one is in French, I apologize. It's actually a French carbon footprint simulator. So you can answer a quiz, which is gonna give you an estimate of your carbon footprint. And so they have a conference mode where a lot of people, for instance, in the same room could answer this quiz. And instead of sending all of their data to some server somewhere to aggregate the data and show it to the conference master or whatever, they're going to exchange it directly in a peer-to-peer manner, which is very nice for two things. First of all, maybe the place where you're having a conference doesn't have internet, in which case, or just a bad internet, in which case it would be hard to share this data with some server to bring it back to the same room. And also, since you're answering some pretty private question in that quiz, maybe you don't want to share this with some company's server somewhere, so this is staying inside the room, basically. When talking about privacy, this example we're going to look at is Tor. So Tor is pretty well known also in the networking community. It's basically to go around censorship and give you more private connection to someone. Instead of connecting directly to someone else, what you're going to do is bounce to a few random hops inside the Tor network, which is going to hide your networking patterns, basically, and the fact that you're talking to someone. So now we know why peer-to-peer is nice, but what does Libp2p give you? So if we take a look at the very oversimplified and wrong history of Libp2p, it all started when Protocol Labs built IPFS, IPFS being like a child between BitTorrent and HTTPS. And when they finished building IPFS, they thought to themselves that building the peer-to-peer part was really hard to do. And what they thought that they could extract all of the Libp2p, the peer-to-peer part of their application and build it into a library and a set of specification, which could then be reused by any other program wanting to build a peer-to-peer application and make it a lot easier to build peer-to-peer application. So we're going to look at what does Libp2p offer you and how it makes your life easier, basically, when you're doing peer-to-peer. So the first thing we're going to look at is the fact that you have multiple transports. So depending on where your application is running, you may have access to some transport or some others. So for instance, the most common transport is TCP. I think everyone working in networking knows about TCP. Another one would be Quick. So it's like TCP with more feature, if I'm being very quick and wrong about it. But these are nice if you are running inside a desktop app or an Android app or whatever, but for instance, if you are running inside the browser, you won't have access to TCP or Quick, and you will have to rely instead of WebSocket or WebRTC, which are meant for the browser, basically, as the name implies. And then you also have more exotic transport. So we talked about Tor previously. You can actually use Tor as a Libp2p transport to make more private connections again. And also, if you are in the same room as some people or close to some people, it might make more sense to directly use Bluetooth to exchange data instead of going through the internet, which is like kind of a big whole thing. And so yeah, this is, for instance, a list of transports handled by Libp2p itself, but Libp2p being one of the implementations, we don't support everything I'm going to show here. So what I'll do is at the end of each slide, I'll show you what are we currently supporting in NimLiP2p, and the rest being work in progress. So for instance, in this slide, Quick is a work in progress, WebRTC is also work in progress, Bluetooth is like far away, something we would like to have, but we are already supporting TCP, WebSocket, and Tor. So now we have all of these transports, which is really nice. Another issue we're going to have in peer-to-peer is NAT, so NAT being network address translation, and NAT is a big issue in peer-to-peer. It's basically a feature of your router which is going to hide your entire private network at home behind a single public IPv4 address, and that's done to save on the number of used IPv4 addresses. But it does mean that if you are behind the NAT, which is most of the time the case, you're very hard to reach from the internet, basically. And so we have a few ways to get around this. So the first one would be to ice your router nicely to make you reachable from the internet using UPnP or PnP. But sometimes that doesn't work, so you're gonna have to go to hole punching, which is a bit more extreme, and basically you're tricking your router into letting connections in. It works sometimes, but not always. And if this doesn't work, you're gonna have to rely on relay, which is basically a third-party server which is going to relay to you every connection that you are expecting, which is less efficient and less efficient, so it's like a last resort thing. And so again, we support UPnP and PnP, we support relay. Hole punching is still a work in progress in the NIM implementation. So now using all of this transport and the NAT traversal, you can connect to a lot of people, which is nice, but then you want to make your connection with them private and secure. And so what we want as properties of this connection is, first of all, it's authenticated, meaning you know who you are talking to and no one else. No one is imposing as the person you are talking to. And secured, meaning no one can read what you are saying to them or modify what you are saying to them. So to authenticate someone, we're going to use the peer ID, which looks a bit like this. It's a cryptographic proof of who you are. So if I told you, this is my peer ID, and in the network you are talking with someone which has the same peer ID, you can be sure it's actually me. And then to secure the connection, we again have a few frameworks available, so TLS, Noise, or CKO, and again, we support most of them. And the last thing we're going to look at here is basically you have these two peers. They establish a secure connection using NAT traversal, transport, and ciphering we just talked about. But this is sometimes pretty heavy to do. So for instance, hole punching takes a few seconds to work. And so what you want to do is, once you have established that connection, being able to reuse it for multiple purposes, and that's what we are going to call multiplexing. And so it's basically inside this big pipe, which is your secured connection, you can have like small sub-pipes to send some bits of data, and it means that you can use the same connection for different purposes. So I could use the same connection to ask you for something while you are asking me something else or whatever. So it's also very powerful. And so again, we have a few implementations in Libp2p, we have YAMX, MPlex, and some transport actually support multiplexing by default, so we will reuse it. And so in NIM we support YAMX and MPlex, but since we don't support Quick or WebRTC, we don't support this yet. And so yeah, this was basically the core of Libp2p. So this transport, the NAT traversal, the secure communication, and multiplexing. And so what's really nice is, once you use Libp2p, this is basically all hidden away from you. You don't have to worry about which transport you are using or whether you need to hole punch or whatever. It's like automatically handled for you. And on top of this, you can start to build these protocols and do whatever you want to do with them. And so we're going to look at a few protocols which are actually shipped with Libp2p. And again, here to make your life easier. So the first protocols we'll talk about are discovery. So if you think about it, you have the whole internet with billions of devices, and you want to find inside the whole internet the few peers and devices which are in the same network as you, or interested in the same things as you. And so you can do this using discovery methods. So there's a few possible ones. So Bootstrap, which is basically having a hard-coded list of peers. DNS discovery, which is going to be the same thing, but with DNS. Rendezvous, MDNS, DHT, etc. And so here you basically have some trade-offs to do on speed, privacy, censorship resistance, etc. And so again, Libp2p ships with all of these to help you do this more easily. And NIM doesn't support all of them yet, but it's again a work in progress. And so once that you have discovered all your peers, maybe you want to do broadcasting. So broadcasting is pretty simple. You have one network with one peer which has one message. So for instance, that message could be an actual text message, but it could be a video, a file, a status update, a temperature reading, whatever. And you want basically to send it to the whole network. And so this is quite hard to do in animators, but even more so in peer-to-peer, because you basically have to balance between latency, privacy, bandwidth usage, attack resistance, etc. And so in Libp2p, we have one protocol called Gossipsub, which basically give you the tools you need to turn some knobs to make something, for instance, more attack resistance or something with less latency. But yeah, so it's trade-offs to do, but you can choose your trade-off basically using this protocol. So again, this is implemented in the NIM Libp2p. So as I said in the beginning, there's a lot of Libp2p implementation which are going to implement the same set of specifications, which means that they're all interoperable in a nice way. And so you have the original one was in Go, you have the Rust one, the JavaScript one, which is going to be used in the browser, or Node.js, you have obviously a NIM one, Python, C++, etc. So some noteworthy Libp2p users, I'll go over them very quickly. IPFS, we already talked about it. Ethereum, you might have heard recently, there was a merge, and so part of the merge was switching to Libp2p, or part of the networking to Libp2p. And status, obviously, we use Libp2p a lot for messaging and other things. And you have others like Polkadot, Filecoin, etc. That's it. So finally, we'll talk quickly about NIM Libp2p itself. So first of all, why do we want a NIM implementation? As you may know, Status uses NIM a lot. We have about 50 full-time NIM devs and 70 public repos. And so most of our end projects have Libp2p somewhere in their stack, so it just makes sense for us to build a NIM native version. And so it's now been used in production for over a year. As you've seen earlier, it has a lot of features for Libp2p implementations. Obviously, it's fully open source. You can check it out, use it in any of your projects. We actually shipped recently the V1, which is giving some API stability. And so on the left, you can find the repo. On the right, you'll find some website which will give you some tutorials on how to get started with NIM Libp2p specifically, teach you some features, etc. And so the last step of this tutorial is basically to build a small Tron example where you're going to use messaging for matchmaking, basically, so to find someone to play with. Then you're going to establish a direct connection between the two and play this little game. So it's actually quite short. It's built with Nico. It's only 150 lines of code approximately, so it's a nice example of what you can do with it. For this presentation, though, I will go into a smaller example just to show you how it looks like to use NIM, the NIM Libp2p. So this is a very simple ping example. We're going to connect to some peer in one network, get the ping between us and them, and print it, basically. It's like hello world. And so you can see at the very bottom of the slide, you'll find the peer ID that we talked about earlier, which is the peer ID of the peer we're going to connect to. Just above this, you'll find its IP address and its port, which we need to connect to him. And so if we look at the getPing method, we're going to start by creating a switch. And the switch is basically going to be your main structure of Libp2p. It's what will hold every transport you have, every protocol you have, etc. Then we're going to create the ping protocol. I didn't mention the ping protocol earlier. It's one of the protocols shipped with Libp2p. It's pretty simple. So. And then we're going to start our switch, connect to that peer, get its peer ID, open a stream to that peer with the ping codec to say that we want to ping him, then ping him, save the result, and show it. So it's, again, very simple, but it's like, again, the hello world and what fits in a slide. But you'll find more and better tutorials on the website. So, thank you. On the left, you find the QR code if you want to check out the Libp2p, the NIM Libp2p repo. Feel free to try it out, start it, and everything. On the right, you'll find my Discord handle. If you want to ask me anything, I'm on the NIM Discord, so you can find me there and ask me any question. And yeah, thank you.